Hello everybody, welcome back to part 4 of our series. In part 3, we learnt about ANN and RNN. So now let us see what is the disadvantage of RNN. So as you can see on your screen, we have taken couple of sentences. So to understand the disadvantage of RNN, we will take an example of NLP, that is natural language processing. So let us say that we have our RNN model and we are trying to predict some words while the user is writing the sentence. So we are trying to basically autocomplete the sentence. So these are the two sentences in which we are trying to predict some words, and these are the training sentences that we have used to train our model. So as you can see, these sentences are almost similar to each other, and let us suppose that these are the two sentences that we have used to train the model. So I like juice, so I went to juice center, and I like pizza, so I went to Domino's. So once our model is trained, we have to predict something in these two sentences. However, while training the model, if you remember from part 3, we had talked about hidden state. So let us say that this is our hidden state, represented by this box having letter H. And so if you remember from part 3, that I had told you that while training RNN model, it stores some sequences from the data that we have used to train, and that sequence will be used while predicting something. So now if you analyze these two sentences, there are two sequences in each of the sentence. So the first sequence is I like something. Now this something can be juice, pizza or ice cream or even coffee. And the second sequence, which is also a pattern of words, is so I went to. Now as you can see, this sequence is repeated even in these two sentences and also in our training sentences. So ideally, while the training process is going on of our RNN model, this first sequence should be stored in the hidden state. However, as the training process progresses, our RNN model will find out yet another sequence, and it will try to store this sequence in the hidden state. But now already the first sequence, which is this I like something, is stored in our hidden state. So it cannot actually store the second sequence as well. So it has to override the first sequence, and it does so and stores the second sequence. So while it does so, since it is overwriting the first sequence, we have lost the first sequence. Now, this is actually a major issue, and let us understand why is it so. So here, if you read this sentence, I like coffee, so I went to coffee shop. Now, let me erase these two words. Here again, let me erase the last two, three words, ice cream parlor. And now, if I ask you in this sentence, what should be after 2? So definitely you will say that it should be nothing else than ice cream parlor. And now let us analyze that how did we understand that it should be ice cream parlor and not something else. So first we analyze this sequence, that is so I went to, and from these pattern of words we understood that there must be some place after this word to that the user wants to write. So in order to analyze what this place actually is, we notice this pattern, which is I like ice creams, which is the first pattern by the way. And here we notice that the word necessary or the keyword is ice creams. So the user might be trying to go to ice cream parlor. So that's how we determine that here it should be ice cream parlor. Now similarly, first in this sentence, first we will try to see what is the sequence. So here we notice that it is so I went to. So here it must be some place, and now to determine which place it is, we again look at the keyword which is present in our first sequence, and that is I like coffee. So here it is coffee shop. However, in our RNN model, as I told you before here, that we don't have the first sequence stored, and we only have the second sequence as it progresses through its training process. And so when it tries to predict this word, unlike we humans, it can't find out that which place actually the user is going to. So here the RNN model will notice this sequence, which is so I went to, and it will understand that the user might write some place after this word too. However, it won't understand that the user will write coffee shop, since it has already overridden the first sequence which contained this keyword, that is coffee. So what actually is happening here is our RNN model is suffering from short-term memory loss, and in order to solve this short-term memory loss, we need something, and that is called as LSTM. Now LSTM stands for long short term memory. So now let us try to understand how this long short term memory works and how it overcomes this problem of overwriting the sequence that is found in RNN model. So here is a detailed diagram of what happens inside an LSTM model. So if you remember, I had shown you a diagram of RNN model, which is this one, and the diagram of LSTM model is also pretty much same. Only difference is what happens inside each of the neuron, and that is shown in this diagram. So here, as you can see, we have something that is represented by hi minus 1 and hi. So this hi minus 1 and hi is actually hidden state, and again we will be using time steps here. So this is hidden state at time step I minus 1, and this is hidden state at time step I. Now in an LSTM model, there is actually another state which is called as cell state, and this Ci minus 1 represents cell state at time step I minus 1, and this Ci represents cell state at time step I. Now if you remember from part 3, I had told you that hidden state is passed on from one time step to the next time step. Similarly, the cell state is also passed on from one time step to the next time step in an LSTM model. So this complete diagram is actually what happens inside the neuron of a LSTM model. Now let us dive deep into this diagram and understand some mathematical operations that happen inside the neuron of LSTM neural network. So now here we have our input, which is represented by xi. So this input is at time step I, and this input and the information from hidden state is taken here, and some mathematical operations are being performed, which are collectively represented by this plus plus symbol. So now let us understand what operations are being performed here. So for these operations, we require two weights and one bias. The first one being WH, the second one being WI, and a bias represented by B. So the information from the previous hidden state will be represented by hi minus 1, and it will be multiplied with WH, which are the weights for the hidden state. So WH into hi minus 1. Then the result of this multiplication will be added to another multiplication, which is WI, the weights corresponding to the input, into the input itself. So xi. Now once we have this, we will add it to the bias. So this will give us some number. Let us represent it by r. Now this r will go through the sigmoid function. So now there is an interesting thing to note here. This sigmoid function will always give an output which is between 0 and 1. So irrespective of the input, the output of the sigmoid function will always be between 0 and 1. Now this output will be multiplied with the contents of the cell state. Now this whole thing here is called as forget gate, as it is written here. Now why this is called as forget gate is, this sigmoid function here decides what part of the information stored in cell state should be forgotten. So the output of the sigmoid function will be multiplied with the contents of the cell state. Now as I told you before, it is always between 0 and 1. So if the output of this sigmoid function is close to 0 and it is multiplied with the contents of the cell state, then the contents of the cell state will become 0, and if the output of this sigmoid function is close to 1 and then it is multiplied with the contents of the cell state, then the contents of the cell state will basically remain unchanged. So this is how the sigmoid function decides if the content stored in this cell state should be forgotten or not. So now let us study what is input gate. So input gate basically decides what information should be stored in the cell state. Remember that forget gate decides what information which is already stored in this cell state should be forgotten, and the input gate decides what information should be stored in the cell state. So now let us understand how this input gate works. So we have our number which is represented by R, and we have got this by performing these mathematical operations. So now we will pass R to sigmoid function as well as tan h function. So we will get some output. The outputs of both these functions will be multiplied with each other, and then the result of this multiplication will be added with the contents of the cell state. Now the sigmoid function again plays a crucial role here in deciding whether the information should be stored in the cell state or not. As I told you before, it outputs something which is always between 0 and 1. So let us assume that the sigmoid function outputs something which is really close to 0. It is so close to 0 that it is safe to assume that the output of the sigmoid function in this case is actually 0. And now if we multiply 0 with the output of tan h, then obviously we will get 0. And if we add it to the contents of the cell state, then the contents of the cell state will remain unchanged. So it is as good as no information is being stored in the cell state. Now let us take another case where the sigmoid function is outputting a value which is really close to 1 instead of 0, and it is so close to 1 that it is again safe to assume that the output of sigmoid function is actually 1. So now if we multiply 1 with the output of tan h, then obviously we will get the output of tan h as a result after the multiplication. And if we add it to the contents of the cell state, then obviously the contents of the cell state will no longer be same and they will change. So here the sigmoid function is permitting the information to be stored in the cell state. So that's how it decides whether the information should be stored in the cell state or not. So now let us understand what happens in output gate. So here as you can see, the contents of the cell state will be passed through tan h function, and also our symbolic letter R will be passed through sigmoid function, and then the output of these two functions will be multiplied and will be stored in the hidden state. So here we have hi and ci. So this represents that the cell state will be passed on to the next time step, that is I, and the hidden state will be also passed on to the next time step, which is again I. Also, the sigmoid function in this output gate helps to decide whether something should be outputted or not. So it decides whether something should be stored in this hidden state or not. So to summarize what is actually happening here, let us say that this is a neuron which belongs to LSTM network, and let us divide this neuron in three parts. So this is the first part, this is the second part, and this is the third part. So this first part here represents input gate, so I. This second part here represents forget gate, so F. And this third part here represents output gate, so O. And let us represent the cell state here, C. And let us represent, okay, C. And let us represent the hidden state here, so H. So now whenever some information is passed on to this neuron, the input gate here will decide if the information that the neuron has received should be stored in the cell state or not. If input gate decides that the information should be stored, then it will be stored here in the cell state. Now in the next part, the forget gate will decide whether the information stored in the cell state should be deleted or not. And if it should be deleted, then how much portion of the information stored in this cell state should be deleted. So once that done, let me represent it by a cross mark. So forget gate has deleted something from the cell state, and once that's done, this output gate will decide whether the information that is now present in this cell state, that is after deletion by the forget gate, should be given to the hidden state. So if the output gate decides, okay, the information should be stored in the hidden state, then this information will now be stored in the hidden state. However, it is very important to note that when the information is being stored in the hidden state from the cell state, the information is not being actually moved, but it is being copied. So a copy of information will be stored in the hidden state, and the original information will also be stored in the cell state. That is, the original information from the cell state will not be deleted. So now, if you remember, I told you that RNN suffers from short-term memory loss. So you have almost understood that how LSTM solves this problem, but let me simplify it for you. So to understand it completely, you should consider this cell state as long-term memory of our LSTM model, and you should consider this hidden state as short-term memory of our LSTM model. So let me represent it by S and L. So this is the long-term memory of our LSTM model, and this is the short-term memory of our LSTM model. So whenever some information here is received by our LSTM model or the neuron belonging to LSTM network, it first decides whether some information or some part of the information stored in its cell state, that is its long-term memory, should be deleted or not. Once that is done with the help of the forget gate, it decides that whether the information that it has received now at this moment, that is at this time step, should be stored in its long-term memory or not. And once that is done, finally it decides whether the information stored in the long-term memory should be used to influence the output. Now it doesn't actually influences the output, that is, this long-term memory doesn't actually influences the output. If this particular neuron feels that it should influence the output, then what it will do is it will store the information from the long-term memory to the short-term memory, that is the hidden state. And if you remember, I had told you in part 3 while explaining the RNN model that this hidden state actually influences the output. So the long-term memory indirectly influences the output with the help of its short-term memory. So that is how we had solved this problem very effectively, and that's why it is known as LSTM, that is long short-term memory. So this name of this model is, I think, very apt for the functions that it is actually performing. This LSTM model is, by the way, also known as extended version of RNN model, and it is very important to understand why is it known like this. It is because the information that is being stored in the cell state and hidden state is nothing else than the sequences and patterns that it has found out or it has determined from the input that we are giving to it while its training process. However, it is not only using the hidden state to store the sequences slash patterns, but it is using the cell state as well to store these sequences and patterns. So it does remembers these sequences and patterns for longer period of time by storing it in the cell state, and hence it is being used as its long-term memory, while the sequences and patterns that it feels should not be that important are stored in the hidden state, and also the sequences and patterns from the long-term memory that it fills should be used to influence the output are also stored in the hidden state. So that is why it's called as the short-term memory. And thus this LSTM model is nothing else than extended version of RNN model. Now, at this point of our series, you must be having a good knowledge about what are neural networks and how do they work, and also about the models of these neural networks. So, there are two important concepts that need to be understood, which are overfitting and underfitting. To understand these two concepts, we will have to take an example, and for that we will take our project itself as an example. So as I had told you before, in our project we are trying to predict the close prices of the Bitcoin. So let let us say that this is the graph of closing prices of Bitcoin. So this is the y-axis, this is the x-axis, and here are the closing prices in USD, and here are the timestamps. Now let me represent the closing prices that are predicted by our model by this red line. So let us say that these are the closing prices predicted by our model, something like this. And let me represent the actual closing prices with black line on the graph. So these are the actual closing prices. Now, as you can see, there is some difference between the prices predicted by our model and actual prices. So these are the actual prices and these are the prices predicted by our model. So the line representing the actual prices when plotted on a graph is above the line representing the prices that are predicted by our model. So this concept here is called as overfitting. So it is said that our model is overfitting the given data. That is the data that we have fed our model during the training process. Now let us understand what is underfitting. So again, let me draw a graph. So this is the y-axis, this is the x-axis, and here y and x. Okay. Let us again represent the prices predicted by our model by red. So these are the prices predicted by our model. And let us represent the actual prices of Bitcoin by black. So these are the actual prices. Now again, as you can see, the prices predicted by our model and actual prices are not exactly the same. If that would be the case, then these two lines would be overlapping each other. However, if you will compare it to this scenario here of overfitting, you will find out that the prices predicted by our model are higher than the price than the actual prices of the Bitcoin. So this line here, which represents the prices predicted by the model, is above the line of the actual prices. So this is what is known as underfitting, and the model is said to underfit the data that we have fed it during the training process. Now we should understand what conclusions should be drawn from these two scenarios. So in this case of overfitting, the model is performing extra well, which is obviously undesirable. And to tone down the model, we need to tone down its characteristics. So basically, we need to reduce the number of neurons present in each layer of the model, or maybe we need to reduce the number of layers itself in the model. This can also be accompanied by reducing the batch size or the time steps. So in this case of underfitting, the model is not performing up to its mark and we need to increase its performance. So this is actually opposite of overfitting, and so we need to increase the number of neurons present in each layer of the model or the layer itself. Also, this can be accompanied by increasing the number of batch size and the number of time steps. So this was all about today's part, and in the next part we will apply all the concepts of deep learning that we have learned in part 3 and today's video. So see you soon in the next part, and thanks for watching.